Recording is rolling. It is Friday, September 9. Right, so here's our agenda today. So we're going to a weekend, trying to wrap up projectile motion here. I still want to do a lab with you guys, but didn't quite get to that this week, so we'll do it next week. But actually, I don't have a note for that, so let me start with that, just to get you guys thinking over the weekend. Right, so I have these launchers. You guys see this launcher right here? Right, it's got a little yellow ball in it. It's got a ramrod stuffer. Right, so you guys see this is gonna be a spring loaded right here. Right, so I can push this in. Right, take this yellow ball, pop it in right here. Right, pull this release, and then it's gonna fly out. Right, yeah, here, demos for you guys. Ow! Guys, that. Right, so this also, see how you can change the angle and see how this bob's hanging down. It has a built-in protractor, so you can adjust the angle like that. Do you guys suppose that you could do some kind of setup where you could determine the blast speed of that launcher? Right, you could probably either do this type setup. Maybe we could head out to the balcony with the stairs. Right, if you do this height, you could bam, see like exactly where it lands and get it. No, right, using the physics. Right, or if you wanted to, this might be a little bit harder, but I bet you could do some setup like this to figure out what the blast speed is. You guys think you do that? Okay. I'll let you guys think about that over the weekend, and then that's what I want to do with you guys on Monday. Okay. And all right, speaking of Monday, I'm going to pick up from you guys your homework. So remind you guys what that was. You guys got this page double-sided, right? On one side are 20 conceptual questions that we covered with a Kahoot, right? So if you missed that day or whatever reason, then remember the video is posted on Google Classroom. Now, this is mostly what I care about for you guys for conceptual physics. On the other side are different projectile scenarios. Look at 6 different scenarios. We solved some of these problems in class, so whatever we solved in class, just have solved on your own paper, so I can just see that you were following along. Okay, so that's what I'm looking for, right? Right. Solve whatever we did in class. You don't have to do the whole side here, right? And then you have the conceptual questions that we did with Kahoot. Right? All right. Oh, I just gave you guys a projectile motion quiz that looks like this, right? So let me go over this with you guys so you know what you're looking at. The first 3 questions are all graph questions based on a cannon sitting at the edge of a cliff and firing a ball horizontally, which, think about it, looks like this, right? Isn't that what the first 3 questions look like? That's the scenario? You guys got that? Okay. Right. Now these graphs, what do they say? Height drop as a function of time. What's the vertical component of velocity as a function of time? And what's the horizontal component of velocity as a function of time? Those graphs for that scenario are in your notes. So if you look back in your notes, then all you have to do is copy paste those graphs. Of course, I mean, ideally, I do want you to know like from scratch how to do them, but I mean, the answer is in your notes. Okay. These 3 questions are conceptual questions that are off that conceptual questions page, right? You guys got those? Right. So we went over this with the Kahoot. Right. Then if you flip this over, the last 3 questions, number 9, 10, 11, are also conceptual questions straight off that page that we covered with Kahoot. Okay. And then there's a pair of questions in the box. You guys see the pair of questions in the box? Let's take a look at that one. A cannon's at the top the edge of a cliff, so many meters above a plane below. Okay, so I told you the height of the cliff. Okay, it blasts a cannonball at horizontally at some speed. Okay, so I told you the blast speed of the cannon horizontally. So this is also a horizontal component of velocity. Okay, I told you gravity is 10 meters per second squared. You guys know that. Okay, and there's a couple of questions. What's the hang time of the cannonball, and how far from the base of the cliff does the cannonball land? Okay, so again, here's a pretty good picture for that scenario. I told you the height of the cliff, and I told you the blast speed. And the 2 questions are, what's the total hang time to get from point A to point B? What's the hang time? And the follow-up question is, how far does the cannonball land from the base of the cliff? This is say, what's the horizontal displacement? How far does it land? Okay, guys, that? Okay. Now we've solved a few problems like that, but just for super extra completion, I will do another one of those with you guys. Okay, and then after we run that scenario. So you can see like exactly what the mechanics are, even though you have it back in your notes too. Okay. We're gonna solve another projectile question, and then we're gonna wind down with a fun Friday science video. But while that's playing, if you guys have any projectile questions, then of course I'm happy to answer any questions you guys have. Okay. So let's do cannon on a cliff. So, right, so I'm gonna draw a cliff right here. Cliff. Right, and here's the ground. Right, get myself a cannon. Gonna blast the ball horizontally. Okay, so that's the picture. Right, here's what the cannonball's gonna do. It's gonna follow a projectile path, like a parabola shape. Land right down there. Right? Okay. Right. So I told you guys the height of the cliff. Now I'm gonna make up a number that is not on anybody's paper, so just so you have a unique scenario here. I'm gonna say the height of the cliff of my cliff for the notes here is 605 meters. Okay, because that's gonna give me some nice round numbers down the line. You'll see why this plays out. Okay. Let's say the blast speed of the cannon, which is v sub x, it's the horizontal component of velocity, which stays the same all the way throughout. Right? Just the horizontal component. I'll call it 50 meters per second. See, something like that. Okay. Okay. So there you go. There's the setup. Of course, you guys know gravity field on Earth is pulling down at 10 meters per second squared. Okay. And there's two questions. One question is, well, how much time is the ball in the air for? And you have to get that question right to answer the follow-up question of, well, what is this horizontal displacement? Like, how far out does it land? How far? Okay. So first question first, how much time is the ball in the air for? Now, of the two given numbers, the height of the cliff and the blast speed horizontal, okay, you only need one of those numbers, one of those values, to answer the question, how long does the ball fall for? Okay. As which number is important to answer how much time the ball is in the air for? The height of the cliff or the blast speed? Height. Yeah, height of the cliff. Height of the cliff, right? Do you guys remember Paul Hugh did the experiment? He had he blasted two balls at the same time. One went straight down and one went out. Which one hit the ground first? They tied. Yeah, same time. Right. The fact that they tied means that the answer to the question, how long is the ball in the air for, is the same as if you just took a cannonball and just suppose there was a cannonball sitting perched right at the edge of the cliff edge. You just gave a little tap, tap, right? You just fell straight down. Right? Wouldn't that be the same time as if you blasted it out horizontally? It's the same time, isn't it? Right? Okay, so we need the height of the cliffs to somehow answer how much time it's been falling for. We know it's accelerating. That matters too. Hey, you know what I'm thinking? I'm thinking that we need one of these three amigos to get us the answer to that question. What's the fall time? Okay, so what's the fall time? I need something that has time in it that immediately strikes out which of these. You can't use which to solve for time. Yeah, the third one. Great. Because I don't see a T here. Right, so that one's out. Right. Eliminated. Right. And something to do with the height of the cliff. Oh, well, the height of the cliff matters. That also eliminates which one? Which one does not have displacement in it? Yeah, the middle one. This is final velocity, this is initial velocity, acceleration, time. I don't see anything that would have anything to do with the height of the cliff here, right? So, okay, so it's got to be the top one, right? We're gonna take this top one and we're gonna modify it. This is some general displacement. This is some general acceleration, okay? But we're gonna turn it all into vertical. Remember, the way we're analyzing projectiles is we're gonna say what's going on strictly horizontally or what's going on strictly vertically. In this case, strictly vertical. So wouldn't the displacement, the vertical displacement, be referring to the height of the cliff, right? So where that x is just some general displacement x, for the specific scenario, I'm going to call it h for the height of the cliff, right? That's what that is, right? Oh, v naught. Now this would be v naught in the vertical direction because I'm just focused vertical to get the height change. Okay. Guys, when this cannonball is leaving the cannon barrel, how fast is it traveling vertically leaving the cannon?
Oh my God, 10 meters.
Okay, so 10 meters per second squared is this acceleration over here. So we will need that number, right? Now, but what about speed, the vertical speed? Is the cannonball moving up or down at all, leaving the barrel? No. So that makes this number what? 0, right? Because this is actually v naught sub y, isn't it? Maybe I should write the expanded version. So like x equals, or maybe like y or something, right? V naught in the y direction, t plus 1/2 AT squared, just to sort of like copy paste what's here, right? Okay. So height is the vertical change, right? The height drop, height lift, okay? This number is just 0 because, remember the cannonball is not moving up or down, leaving the barrel. Now, let some time roll forward and it starts moving down, but leaving the barrel, this is just 0. Okay. And then 1/2, but we have a special kind of acceleration. G, acceleration due to gravity, that's your 10 meters per second squared, right? And then for some time squared. Is that true? Right? Is that okay? Great. So, oh, look at this. H equals 1/2 GT squared. That should look super familiar, right? That's if you release the ball from rest and count off how much time, you can know how far it falls. Or if you know how far it falls, like in this case, you can back calculate how much time it was falling for. Okay. So I'm gonna plug in my numbers. I've got a 605 meter tall cliff. You guys just told me gravity is pulling at 10 meters per second squared. And then we can use this to solve for time. Right? Okay. Did that check out? So that's okay, right? Okay. Everybody good? All right. Now we need to do a little bit of algebra, right? So you gotta know some algebra for this class, right? So get some good practice right here. Half a 10, what's half a 10? Okay, 5? Maybe I'll rewrite this. I'll go 605 meters equals 5 meters per second squared, because half a 10, times t squared. Okay, so that didn't do very much, but I guess a little bit. Right? I'm thinking we're 2 algebra steps away from solving for t. What's the next algebra step I have to do? Divide both sides by 5 meters per second squared. There you go. There you go. All right, so you know, I'm gonna swap both sides for a minute. So t squared is whatever 605 divided by 5 is. So it's
21.
You got it. So you said
121.
121. Actually, that sounds right. Yeah. So 121. All right. So t squared is 121. And the meters cancel. And we get square seconds. Okay. And what's the very last algebra step? To solve for t, you need to do what? Square root. Can you guys square root both sides? Okay. So if I square root that, I get t. If I square root this, okay, I'm getting a time of 11 seconds. Okay, so that would be the answer to whatever number question that is, right? That's the fall time. That's however much time's in the air. It takes 11 seconds to fall this distance, therefore 11 seconds to get to this point. Okay. Is that okay? Okay, now that I know how much time it's been in the air for, it's been a projectile for 11 seconds, could you combine that with how fast it's traveling across and get how far it's gone, right? So now horizontal component of motion for projectiles, is there any acceleration or does it go constant velocity across the field? It's going constant velocity across the field, isn't it? Right? Because let's see, gravity doesn't pull horizontally, gravity only pulls vertically, but we took care of that already. And we've been ignoring air drag, so let's keep doing that. So can I say just how far it goes is equal to how fast across times the amount of time, right? In fact, this one I bet you guys knew before you ever stepped foot in this classroom. For example, if you're going up I-95 at 70 miles an hour and you do that for 3 hours, how far have you gone? Yeah, 210 miles, right? 70 times 3 is 210, right? Okay, you guys remember that, right? But the only difference here is we're just doing metric units and we're going to solve for time knowing this and this. Or sorry, scratch that. We know time. I'm being silly. Okay, take it back. So we know the ball is always going across the field at 50 meters per second. And it does that for, in this case, 11 seconds. Oh, you know what I meant to mention too, just like super overkill, is that x equals vt is also a modified version of this top equation. If acceleration is 0, which it is horizontally, so it just boils down to that, x equals vt. Right. Okay, so a little overkill there. But, all right. And now all I need is this here calculator. We do 50 meters per second for 11 seconds. That gives me 550 meters. Ba-boom. Okay. You guys think you could do the same thing with your numbers? Right? Because you guys have the same scenario, same picture, right? So we got the vertical information to figure out how much time. Once you have the time, you can go to horizontal, figure out how far it went. Okay, step by step. Right. That's good. Okay. So call this vertical, squeeze that up there, call this horizontal. Right, so this is all vertical stuff on the right side, and then that's what we did first, then switch over to horizontal. There you go. Okay. All right, you guys ready for another review question? Okay, let's do a kick a football question. Go on, kick a football. So got here at the ground, got ourselves a football, it's got some laces. And I'm gonna kick this football with a certain speed at a certain angle. That could be like a velocity vector, right? Speed and angle, that would give you a velocity. Okay. All right, I want my numbers to work out pretty good here. Okay, let's go 50 meters per second. I'll call it V kick. Be 50 meters per second. And let's call this a 53-degree angle, which hopefully that's ringing some bells. It's a very special angle, right? Do you guys think this football is gonna go and land like right about there? Okay. And my question is, where is there? What is this distance x? Right. This one's a little harder than the last one I did, but some good practice. We're gonna get some vector component practice. We'll do it, right? You guys go with the premise. You know how hard you're kicking it, at what angle, it's gonna land somewhere, and you guys know we're in Earth gravity. Because that's where footballs are. So what's the very first step to solving this problem? This is gonna be a process question, right? What's the first step in the process? Should I take this 50 meters per second and break it into components and say what's going on strictly horizontally and strictly vertically? Right, like 50 meters per second, kind of up and to the right. Well, how much up and how much to the right? Right. So I'm gonna make a right triangle. Okay. Dash off some components. Okay. This should look super familiar. We've done this a lot in this class, right? Dash off some components. Okay. How much up? How much to the right? Right. Right. Because once I know that, here's my v sub x, and here's my v naught y. Right. Then I can go to those equations to make sense of this. I can analyze it. What's going on vertically? What's going on horizontally? Okay. Now here's where the trigonometry comes in. You guys remember before we ever did any kinematic stuff, I set you guys up with some trigonometry? Yeah, and I mean, here's one reason it pops up all over the place, right? So how do you solve for v naught y? It's v kick multiplied by what? Sine or cosine of 53 degrees? Sine. You guys remember that? Remember doing this? Right? How about v sub x? That would be v kick multiplied by cosine of 53 degrees, right? We've done this a bunch, so hopefully by now you're getting pretty comfortable breaking vectors into components, right? You do that, right? Let's get some numbers. I'm going to put 50 meters per second here, right? So 50 meters per second multiplied by sine of 53 degrees. 50 sine 53. Look at it, 40 meters per second. Maybe I should have asked you guys. I should have asked you guys before I ran the calculation. What would that be? I bet some of you guys noticed that's going to be 40, and this one down here is going to be what? 50 meters per second times cosine 53 degrees. Are you guys seeing why I chose that very special 53-degree angle? Pop in a cosine where the sine used to be. 30 meters per second. Okay. Okay, guess that? Right. Because guys, this is a what triangle? 3, 4, 5. You guys see a 3, 4, 5 proportion triangle? That's why I did 53 degrees, right? By the way, the other angle I could have picked was a 37-degree angle. That would also result in a same proportion triangle. Right? All right. So when you kick it at 50 meters per second at a 53-degree angle from the horizontal, when the ball is leaving your foot, it's moving up at 40 meters per second. Now, of course, that immediately starts to slow down because of gravity. Right? So that's how fast leaving your foot strictly upward. And it's always moving across the field at 30 meters per second the entire time. It's 30 meters per second. All right. Oh, well, if you're trying to answer the question, how far does it go? I mean, we know how fast it's going across, so if only we knew how much time you could do, this distance is equal to this fast across times however much time, right? Is that true? Is that? But how are we gonna solve for time? So it has to do with one of these components, either the 40 or the 30. Which component will tell you how much time it's in the air for? How about this one right here, right? Because however fast it's going up, right? See, like the fast is going strictly up. See, like, what if you just took a ball and threw it straight up at 40 meters per second? Wouldn't it have the same vertical motion as this football? Right? Because everything accelerates vertically the same, right? All right, so I'm gonna do this a couple of ways to solve for time. But you guys know that's the next step in our next stepping stone, and ultimately figure out how far it goes, how much time it's in the air for, right? So I'll take you guys through second by second, and then we'll do it a different way using an equation, which actually be kind of the same way, right? So, guys, after 1 second, how fast is it traveling strictly upward? 40 minus 10 is 30. After another second, you're down to 20. After another second, you're down to 10. After another second, you're down to 0 meters per second. Now it's strictly vertically. Wouldn't that be the peak? So let's say 40, 30, 20, 10, 0. How many seconds is that? Is that 4 seconds to reach the peak? Is that 4 seconds? Ah, so it takes 4 seconds to get from here to here. Oh, if it takes 4 seconds to get to the top, how many seconds does it take to get back to the bottom? Yeah, another 4 seconds. So what's the total hang time? 8 seconds? Ah, okay, so you could get 8 seconds for hang time, right? Well, let me do the equation version of that if you want to see an equation, right? Now there's multiple equations you could set up so you get to the answer, but one way is you could go final velocity in the y direction equals initial velocity in the y direction minus gt, which is just a modified version of this second kinematic equation right here, this guy, right? Now, instead of plus AT, I did minus GT. Why? Because you picked the ball kind of up, gravity's pulling down, and it went ahead and embedded the negative sign. It's got opposite directions. Okay. Now, if it goes up at 40 meters per second, guys, up at 40 meters per second, use some symmetry. It's landing on the ground. Isn't it coming down at 40 meters per second? So this is going to be negative 40 meters per second, right? It can't jump this fast. It's landing at this fast. 10 meters per second squared for some time t. Okay, guys got that? So subtract the 40. We're going to do 2 algebra steps. Can you guys do 2 algebra steps with me? We're going to subtract the 40 over, get negative 80 meters per second is equal to negative 10 meters per second squared times t. Right? And then what's the last algebra step? Divide both sides by negative 10. Yeah. So time then is whatever negative 80 over negative 10 is. Meters per second squared, the meters cancel. Okay. Ah, you guys see it? That's 8 seconds. Hey, that's what we got before. Using the counting method, we're going second by second, right? Where we got hang time of 8 seconds. Same thing, right? And this is not even the only way to do it. There's other ways you can do it too, with those other equations. Be a little creative. So last question, we're going in for the finish here. How far, I should have listed that question. Let me spell out that question. How far x does the football go? Right. What's the horizontal displacement? Is maybe the more physics way to say that. Right. Can I finish this off with? I think I can put it right here. This piece of paper. Guys, what equation should I write? X equals what? V sub x times t, right? And this is what we just did before, right? For the last question. See that? Okay, so how far it goes? Right now, how fast is it going across the field again? Yeah, 30 meters per second across the field. Right, that's this right here. Comes from 50 cosine 50 degrees. Right, so 30 meters per second across the field, and it does that for how many seconds? 8 seconds. Ah, put it all together. How far did my football go? 240 meters. Well, I guess it's everybody's football, right? Because they just came up with this from scratch. So there you go. Okay, that's the horizontal displacement. That's a ridiculously long distance, by the way, but That's because I get really fast figure speed. So just to translate this back to American, this is over 100 miles an hour, and this is like 2.5 football fields. So yay, I have a super kicker here. It's like Captain America. All right, you guys good? Right. Who's got any questions about anything? Any questions about anything? You guys pretty set for this weekend? Right, that's it. All right. Oh yeah, listen.
I'm confused about everything.
Ah. Well, tell you what, let me do this. I'm gonna wrap up this video here. I'm gonna play a fun science video for you guys to wrap this up, and then I'll go over here and answer any questions you have. All right, and that will be a wrap on the week.